Hello everyone, welcome again to the channel. My name is Amos from Acoustics. In today's video, I'd like to answer a question that I get a lot from my fellow studio owners. It's something to do with the bad bass in the small room. A lot of studios in bedrooms or small home studios have problem with bass response. So I'm here to really explain to you what really happens based on journals and research that were done years back and have been proven not once. Now, what really happens with the small rooms that makes them so difficult to treat in terms of low frequency is that we have wrong room dimensions or room ratios, and then also we have the wrong room volume. So these are two things that happens that makes it so difficult for low frequency to get balanced into the room as it should. So let's get into the room dimensions or room ratios, and this will explain to us what really happens. So when we look at the room ratios, it's responsible for room model distribution, how the room modes are distributed into the room. So before we proceed, we need to understand what room modes are. There's a video I did on room modes, and I'm just going to go over it again. Meanwhile, I'm going to link it down there. If you've not watched it, you can check it out. The room modes is just a basic introductory to room modes. So let's proceed with the explanation of what room modes are for those who don't understand it, and because from there, we are going to understand what really happens in the room and how to go about it. So room modes are caused when wavelengths of low frequencies, we have frequencies with very long wavelengths that cannot fit into the room. Then when they don't fit into the room, or when they are longer than the dimensions of the room, then some of them will escape the room, some of them will bounce back as echo, and then some of them will just create these regions of peaks and nulls across the boundary of the room. And this is very evident if you walk across if you're in a studio right now and you walk across the room, you will hear that some parts of the room have loud bass. If you play a music with the balanced frequency response, you realize that when you walk towards the rear wall, the bass builds up towards the rear wall. You come towards the middle section of the room, the bass kind of dies down. When you move towards the front wall behind the monitors, or if you're in a hi-fi system kind of environment, then the bass builds up in that area. The same thing happens on the side walls, and the same thing also happens on the floor to ceiling. So we need to understand the kind of room modes that take place in the room, and then we'll be able to find solutions. So we have three types of room modes that happen at the same time in the room. We have axial room modes. These are room modes that occur between parallel surfaces. We have front to rear, side walls, and then floor to ceiling. And this is what I just explained, whereby these regions have high peaks and valleys across the frequency response. So we have also tangential room modes. Tangential room modes are found in corners or where two walls meet. And that's why you see a lot of companies advocate for placement of bass trap in these areas, because there's build-up of tangential modes in these areas. And then we have the oblique. Oblique, they are the weakest actually. They occur where the three walls meet, where we have the three walls, the corners where we have the three walls, not really two. So if you understand this, then it becomes very easy to understand what goes on inside these small rooms, which make them so problematic. So the strongest of all these room modes is the axial modes, which I talked about, the parallel surfaces, followed by the tangential across the 90 degrees, and then oblique, of course, the three where the three corners meet. So we need to understand very clearly, and also we need to quantify what really happens and which frequencies are problematic. In the video on room modes, I laid out the procedure on how to calculate the room modes, and also I'm going to do it in this video again, just to make things a bit clear. So we want to use a model room of length 12 feet, a width of 10 feet, and a height of 8 feet. And we want to find the fundamental axial mode that happens across these frequencies. So what you do to find the frequencies that cause problems across this dimension is to take the speed of sound. I like using 1130. And then you divide it by that dimension times 2. In the other video I divided it by 1, but in this we are going to divide it by 2, because that sound wave travels twice. It goes and comes back reflected, and that's how we end up with these room model issues. So if it is a length of 12 feet, we are going to take 12 feet, and then we are going to divide that by 1130, which will give us 47 hertz as the lowest resonant frequency in that room at that dimension. So that's the first actual room mode that happens at that dimensions, 47 hertz, 1130 feet per second speed of sound, dividing by twice that dimension, which is 24. We get like 47 hertz. We have side walls, which is 10 feet. We find the fundamental at that a dimension, which is 1130 feet per second divided by 20, and that gives us 56.5 hertz, which is the lowest resonant frequencies across the width of the wall. And they happen at the same time And then we have floor to ceiling dimension, which is 8 feet. So we take 1130 feet per second, which is the speed of sound, and then we divide it by 16, which is 8 feet times 2. We get a 70.6 hertz. So these are the lowest resonant frequencies that happen in the room, and they happen at the same times. And this explains why small rooms have problems with this kind of dimensions. So we can proceed with that, and we have what we call the fundamental, which is the lowest, which I just explained, and then we have the harmonics. Harmonics are like the offspring of these fundamental frequencies. So let's get into this calculator and find the harmonics for these frequencies, because all these are problems that will lead to bad bass into the small rooms. So let's get to it and calculate it. So we find that after getting the fundamental of 47 at the 12 feet length, we will find its next resonant at 94 hertz, and another one we just add 47, which is 141, and that's how it goes. So we have the resonant frequency at 47, and then second order at 94, and then the third order at 141. The same thing happens on the side walls. We have fundamental 56.5. We have the second at 1130 second harmonic, then we have third harmonic at 169.5 hertz. So that's how you calculate, and you know what really goes on in the room. Now, how do we treat this problem? So that's what we are going to get into next. So stay tuned.